This is a technical synthesis of Aerospace AC Principles, from component physics to systems diagnostics. It is designed as a high-density review for the NCAT Avionics Electronics Technician certification, targeting the experienced professional.
The fundamental engineering trade in aerospace power is AC versus DC, a direct conflict between power loss and weight. DC suffers from severe I-squared-R power losses over the aircraft's longitudinal axis, mandating heavy-gauge wiring. AC's primary advantage is its compatibility with transformers. Stepping up voltage reduces current, mitigating power loss, and, most critically, enabling lighter wiring harnesses, an absolute necessity in airframe design.
Each AC waveform typology has a specific function in avionics. Sine waves are the natural output of generator rotation. Square waves are fundamental to digital logic, forming the basis for data bus communications like the ARINC 429 standard. Sawtooth waves were historically essential for CRT sweeps in legacy radar systems, and triangular waves are used for specific analog-to-digital sampling and conversion.
0.707. This is the root mean square, or RMS, value. Derived from 1 over the square root of 2, it represents the effective value of an AC waveform, the equivalent DC voltage required to produce the same heating effect. 0.636, the average value constant, derived from 2 over pi. This represents the average of all positive instantaneous values in a single half cycle. 1.414, the peak conversion coefficient, the square root of 2. This is the multiplier used to determine peak voltage from a known RMS value.
This is a critical examination point and a universal aerospace standard. Unless explicitly designated otherwise, all avionics AC voltage and current values are assumed to be RMS. Misinterpreting this standard leads to gross miscalculations of power and circuit parameters, a non-trivial error in any high-reliability system.
We now transition from waveform characteristics to the quantum and electromagnetic principles governing reactive components.
Capacitive energy storage occurs at the quantum level through dielectric polarization. The dielectric, an insulator lacking electrons in its conduction band, responds to an electric field not by conducting, but by distorting its internal atomic structure. This distortion creates microscopic dipoles, which is the fundamental mechanism of energy storage in an electrostatic field.
3 primary mechanisms define this process. First, electronic polarization, the distortion of the atomic electron cloud. Second, ionic polarization, the physical stretching of the crystal lattice, common in ceramics. And third, orientational polarization, the physical rotation and alignment of permanent dipole molecules, as seen in tantalum oxide. Critically, the molecular friction inherent in this rotational process is the direct origin of equivalent series resistance, or ESR.
For inductors, counter-electromotive force, or CEMF, is a direct consequence of Faraday's and Lenz's laws. The equation VL of T equals L times di dt is precise. The instantaneous induced voltage is the first derivative of current with respect to time. This is not mere opposition, it is a reaction directly proportional to the rate of change of the current.
These abstract physical principles are embodied in hardened hardware governed by stringent military performance specifications designed for extreme operational environments. Under MIL-PRF 39014 for ceramic capacitors, several parameters are non-negotiable for high-reliability systems. The S failure rate level, 0.001% per 1,000 hours, is the benchmark for flight-critical applications. The BX dielectric characteristic ensures stability across the entire -55 to +125 degrees Celsius operating range. And the strict 60% voltage derating is a mandatory aerospace standard to prevent long-term dielectric breakdown.
Similarly, MIL-PRF 27 governs inductors. Grade 5 encapsulation, molding and epoxy, provides resistance to shock and moisture. Of particular importance is the Class V thermal rating, specifying 155 degrees Celsius maximum temperature. This is a direct engineering response to the extreme thermal environments found in applications like engine bay-mounted FADC units.
We now apply this component-level knowledge to circuit analysis and FAA-approved diagnostic procedures.
The universal time constant, tau, governs the transient response of all reactive circuits. It is the time required for a parameter, voltage in a capacitor, current in an inductor, to change by 63.2% of the difference between its initial and final values. A component is considered fully stabilized after 5 tau. Here is a typical NCATT conversion problem. An avionics signal generator outputs a sine wave with a measured peak-to-peak voltage of 340 volts. The question is, what is the approximate RMS voltage? The critical trap here is the distinction between peak-to-peak and peak values.
The correct answer is B, 120 volts. The rationale: peak voltage is peak to peak divided by 2, so 170 volts. RMS voltage is peak voltage times 0.707, which equals 120.19 volts. Now, for the distractor deconstruction. Option A results from incorrectly using the average constant. Option C is the result of failing to convert from peak to peak before applying the RMS formula. Consider the in situ diagnosis of a leaky coupling capacitor, a common failure mode. 1. Safety protocols. Ground the LRU, discharge high voltage caps. 2. Instrumentation. Set your DMM to measure DC volts with high impedance. 3. Execution. Probe the input grid or base of the receiving amplifier stage. 4. Failure indication. A positive DC voltage reading indicates the dielectric of the upstream coupling capacitor has failed, leaking DC from the previous stage's plate and disrupting the bias of the current stage. We now synthesize these principles and components to see how they integrate into functional aircraft line replaceable units. A primary example of system integration is the Transformer Rectifier Unit, or TRU, within the ATA Chapter 24 framework for electrical power. Its function is to convert the aircraft's AC power to 28-volt DC for main power buses. The use of 400 Hz is a deliberate engineering choice. This higher frequency permits smaller, lighter magnetic components, which saves critical aircraft weight. Inside the TRU, heavy-duty MIL-PRF-27 inductors and MIL-PRF-39018 capacitors are integrated into a robust LC low-pass filter. This network's entire purpose is to smooth the rippling 400 Hz rectified output into a pure, flat, 28-volt DC for the aircraft's main buses.
We conclude with a non-obvious but critical threat in modern avionics: tin whiskers, a problem rooted in material science and regulatory changes.
The issue stems from pure tin finishes, sometimes mandated by RoHs compliance. Under compressive stress, these finishes can spontaneously extrude microscopic conductive filaments, tin whiskers. The failure mode at altitude is catastrophic. A whisker-induced short does not simply blow a fuse, it instantly vaporizes, creating a sustained metal vapor arc, a plasma, that destroys adjacent hardware. The aerospace mitigation, mandated by SAE standards like GIA-STD-00052A, is the use of a tin-lead alloy with a minimum of 3% lead, which quenches whisker growth. This leads to a final, forward-looking consideration. As avionics increasingly integrate commercial off-the-shelf components using non-aerospace materials, how must diagnostic protocols evolve to predict and mitigate novel, system-level failure modes that fall outside the established MIL-SPEC framework?